Hello everyone, welcome to this video. In this video, we'll be looking at the utility of the fundamental theorem of homomorphism through the help of an example. So here, if you remember, in the previous classes, we have studied about wrapping function. In particular, in trigonometry, we have studied about this function, right? We denote it by this symbol W, capital W, right? What does it does? It wrap whole of the real number line to the unit circle in a plane which is centered at the point 0, 0. What does that mean? It means you have your whole real line starting from minus infinity to infinity plus infinity with all the points in between, right? It is being now mapped to a unit circle on the coordinate plane, right? This is your x-axis, this is y-axis, this point is 0, 0, the center is 0, 0, the radius here is 1. So this point basically would be 1, 0, this point basically would be 0, 1, this would be minus 1, 0, and this would be 0, minus 1, right? So this is your unit circle. Not the disk, we are just taking the boundary. So this is your unit circle. So you see this line is now mapped to this unit circle. How it is being mapped? They are saying that the number 0 on the number line is mapped at the point 1, 0. So here, if you have number 0 here, this is mapped to this point, right? Next, they are saying the positive reals are mapped in the anti-clockwise direction. So that means whole of your positive reals, they are mapped starting from this point in the anti-clockwise direction. Now because there are so many numbers, so they keep on rotating like this. So they would repeat its value after a certain interval, correct? And but we have to move from this point here 1, 0 in the anti-clockwise direction, right? Similarly, for the negative reals, they are saying they are mapped in the clockwise direction starting from the point 1, 0. Right, so all these negative reals, they are now starting from this point 1, 0 are going in the clockwise direction, right? They keep on rotating as the values increase, right? And this is how you obtain all the values. So this function is wrapping whole of the real number line to the unit circle in a plane with center at 0, 0, right? I have shown here diagrammatically, this is our real line and this is our unit circle. Right, in this unit circle, you can clearly see the point 0 is mapped to the point 1, 0, right? This blue portion which represents the positive real axis, starting from the point 1, 0, it goes in this direction in the anti-clockwise or the counter-clockwise direction, and it keep on going like this until we are finished with all the real numbers. And you know, we never have a finite number of real number, hence we keep on rotating like this until we reach to a value that is satisfactory for us, right? Similarly, for the negative reals, if you start from here and go, so what you do, you starting from the point 1, 0, now you move in the clockwise direction. So from here you start and keep on going like this until you reach some satisfactory point where you wanted your value, correct? So here you see this 1 here is mapped to this point, right? This 2 here is mapped to this point W. This is W of 2. The point 3 is mapped to W of 3. The next value would be somewhere here. The next would be somewhere here, and so on. We keep on doing like this. So again, the values would repeat after sometimes because the function is periodic, correct? In a similar fashion, you have the number -1 plotted over here, correct? And so on. -2 would be somewhere here, -3 would be somewhere here, and so on. So this is how you plot this particular function, right? In general, this function W assigns to each real number A the point A radians from the point 0, 1 on the circle, correct? So here you see we have what? You know, the angle theta is defined by arc length divided by the radius. Now in this case, because the value of radius is equal to 1, because we are taking the unit circle, so it is just equal to arc length. So you see, whatever arc length we have, whatever is the distance from here to here, the same is being covered here. So whatever is the angle covered by this, that is same as this distance, right? So that is how they are defining it over here, and they are saying that to each real number a, we have a radians from the point 0, 1, correct? So basically now we say that this mapping W from the group of real numbers where addition is the group operation to the circle group where we have multiplication as the group operation. Now what is this circle group? This is the group of complex numbers. Because why? Because we are in the coordinate plane with 2 dimensions with having magnitude 1. So we now say this mapping is a homomorphism. Let's see how. Does it follow the operation preserving property? Let's verify that. In order to verify that, what we wanted to do, we wanted to check W of, if we take 2 elements x and y, here the group operation is plus. So when you perform W of x plus y, it should give us W of x. Here the group operation is multiplication. So W of x into W of y, right? This is what we wanted to check. Let's take the left hand side first. So here it is quite obvious that we can define it like this. W of x is cos of x plus iota sine of x. Why? Because both of them, they give you the values lying on the unit circle. This is how you define the unit circle. So what would be W of x plus y? It would be cos of x plus y plus iota sine of x plus y. Now you can expand cos of x plus y and sine of x plus y using the trigonometric formulas, right? And now from these two terms, this one and this one, you can take cos y common, so you'll be left with cos x plus iota sine x, right? Similarly here, instead of writing -1, you can write plus iota square. There is no issue. Now from this term here and this term here, you can take iota sine y as common, right, from here. So you are left with iota here cos x and here iota sine x. So that now you see this and this are common in both, so you can write it like this, and you are left with cos y plus iota sine y. So the first one is your Wx, the second one is your Wy. Hence you have proved that this forms a homomorphism. Correct? Now if this forms a homomorphism, so what is the kernel of this mapping phi? So we see W is a periodic function having period 2 pi. So what would be the kernel? We say the kernel would be the one which is generated by 2 pi. Why this is so? Because by the definition, because your wrapping function goes from R to the circle group, we need to find what is the identity of the circle group. So you see the identity of complex numbers having magnitude 1 under multiplication, its identity is 1, 0. So kernel of W would contain all those x from the real set of real numbers such that W of x is equal to what? 1, 0. So by the definition of Wx, we have cos x plus iota sine x here. So equating both the sides, real and imaginary parts, you get cos x is equal to 1 as well as sine x is equal to 0. And both of them happen simultaneously whenever we have some multiple of 2 pi. So that means you have a subgroup which is generated by 2 pi, right? So this is your kernel. Now once you have your kernel and you have a mapping which is a homomorphism, you can apply the fundamental theorem of group homomorphism. According to it, you have the group R, the factor group of R generated by this kernel 2 pi, right? Because you know kernels are normal subgroups. This is isomorphic to the circle group, and this is the result that we obtained by using this fundamental theorem of group homomorphism. So I hope you understood this example well. Well, that is it for this video. Thank you for watching.